All right, well, welcome back. During the break, we opened the doors, as you saw, and we've also opened some windows and switched the heating off. So hopefully, everyone will be able to stay awake until 5 o'clock when you finish. We have two presentations left for the rest of the afternoon. The first of these is an industry perspective, something a bit different from what we've seen so far today, which comes from Stefan, who is now at Siemens, but formerly was at Altair EDEM. So Stefan will be telling us about his experience combining DEM and AI. So over to you, Stefan.
Thank you. Thanks for the introduction. Also, before I start, I want to thank JP for inviting my boss, Carlos Lavra, today. Couldn't make it, unfortunately, so I get to meet you all, which is excellent. I've already learned much from the talks. So my name is Stefan Pantaleev. I'm a lead solution specialist, formerly at Altair EDEM, now Siemens, still Altair EDEM, but under Siemens. And my experience primarily comes from industry, so I spent around 10 years now, all told, doing DEM. 7 of those in industry. And I've worked with a large number of customers, wide range of industries, pharma, battery, so spanning different particle sizes, from very fine powders to very large particles. And what I can share is what I've learned, some of what I've learned during that time. As Professor Windows you was saying, and I agree with him, there is much less knowledge in industry about applying DEM, certainly. And part of my job was to help some of the customers do things better, and there are some notable exceptions. Some customers that are extremely knowledgeable, but they come from academia, typically. Some of them are in this room. One correction, final correction before I begin, it was a typo. Maybe a small or big typo, depending how you see it. There was a doctor in front of my name. I can't claim to be your peer in terms of academic qualifications, so not a PhD, just to be clear. Kind of JP to add that if it wasn't by mistake. But hopefully I'll tell you something interesting about how things are done in industry. I'll give you a bit of an introduction since I'm new. You may be new to Siemens, so I'll tell you very briefly about us. And then I'll talk about how we leverage AI with DEM and why. And there are really 3 main ways: simulation-assisted AI, AI-assisted simulation, and agentic AI. And really the examples that I'll give are very similar to what was presented in the morning. And I'm grateful to the speakers for providing a lot of detail. So my talk is a broader overview, and I'm not going to go into such detail, but the methods are very similar to what was presented, with some minor differences. And then agentic AI, I'll touch upon that. And finally, our perspective on what makes a DEM called AI ready. So how are we preparing to leverage AI with DEM to a greater extent? So why combine DEM with AI? First, very briefly about Siemens. As part of the large mother company, which I'm sure you've heard of, there is a sub-company called Digital Industries, which focuses on software technology, and I work in the software division of that company. It's its own company, headquartered in Texas. And that company was very aggressively grown through acquisition, which is a trend we see in industry today with simulation software and, well, generally technology. Because of the complexity of the problems that the customers are facing, the solutions are multi-physics, multi-method, and also require compute and require IoT. So a very broad portfolio of tools is required. The customers don't like to deal with multiple vendors. They don't like to integrate multiple vendors together, so they're looking for a one-stop shop for all those tools and interoperability between between the tools, and that is why in the recent years we see very aggressive agglomeration of software vendors into small number of massive players. And we come, so Altair EDEM comes into the Siemens family through the Altair acquisition, which was recently finalized. It's a $10 billion acquisition, the largest that they've done so far. And this makes Siemens Digital Industries the #1 industrial software, I think, probably per revenue. Looking at the revenue, that's probably realistic. 6.3 billion last year. This year will be higher because of the Altair acquisition. Our portfolio is very broad. Now the Siemens combined portfolio is very broad. Altair's portfolio was quite broad on its own, spanning simulation, AI, high-performance computing, and IoT. Now with Siemens, we have even greater breadth of tools. I won't go into detail other than to say that Altair is part of them, somewhere in the simulation portfolio. That is the Sim Center line of products. EDEM was mentioned kindly before. I'm sure that a lot of you are familiar with EDEM. It was the first commercial DEM code, still extensively used in academia also, but more so in industry, I would say. And this is where I work as a solution specialist. Okay, so before we go into how we use DEM and AI, I find it always useful to just remind ourselves what the customers actually want. And it's very different to, I think, the needs of academia. But our customers essentially want to do things faster, cheaper, and better. And that means reducing time to market and development costs, reducing waste, energy, materials, so doing things more efficiently, improving performance and operations. But really, the time to market is, in my experience, the primary concern in a very wide range of industries. Okay, so doing things more efficiently matters. Improving performance is always important, but time to market is really crucial today in a wide range of industries. And this brings us to how our customers use DEM. And Professor Windows Yu, he did mention that the knowledge in industry is limited and that the models are imperfect, and that's right. That's exactly right. But we do have a notable exception. We have a small number of customers which seek fundamental understanding. They would run a small number of simulations which are well calibrated, experimentally validated sometimes or most of the time. And they'll perform a more sophisticated analysis on those simulations. So if you look at an example of a blender, they might compute fundamental quantities like the granular temperature or the momentum density and try to understand the underlying mixing phenomena, the dominant mixing mechanisms and so on, and then use that understanding to solve problems. And I've been fortunate to work closely with a lot of those customers. But the reality is that the majority of our customers simply perform virtual trials. They perform virtual trials with very simple models, poorly calibrated models, models which no consideration has been given, or not much consideration has been given to coarse graining or validation really. And the goal of these models is not to have quantitative accuracy, it's not to develop understanding, it's to inform physical trials. It was mentioned that in industry there is a degree of conservatism, and that's absolutely right. People still don't have a high degree of confidence in simulation. People like the physical trials, rightfully so. And so, physical trials are never going to go away or even be significantly reduced, but they can be informed. And so the purpose of these simple models is simply to provide a useful guess as to what should be tried physically. And this is how we make most of our money, because running virtual trials requires a lot of compute, a lot of usage, a lot of units. and that is why we're focusing on the needs of that component, of that segment of the customers. Okay, and so with this in mind, what do they need, and how does this relate to DEM codes? First and foremost, they need efficiency, and by the way, we have significant gaps today between what they need and what we can provide, and purely with simulation. And those gaps are not going to be closed anytime soon, but we can try to partially bridge them with AI. And one of them is efficiency, so the ability to run tens of virtual trials rather than hundreds. And here we can leverage simulation-assisted AI in much the way it was described, and I'll show you some examples too. We need speed, so really now customers are demanding seconds of runtime, but certainly not days. Seconds for real-time model-based control, for example. Obviously, with DEM, that will be challenging. And they're demanding accuracy, and the accuracy, in my experience, in our view, actually particle size is the primary challenge. Of course, physics is important, right? And having the wrong contact model would affect the simulation negatively. But it's even worse when you don't coarse grain properly. And the problem is that coarse graining obviously is complex. You have to worry about how to scale the micromechanical parameters to maintain the micromechanics. You have to worry about inertial effects. You have to worry about maintaining the fabric, so bottlenecks and jamming. There is no universal set of coarse graining rules across flow regimes and stress states. There's trade-offs. Often systems exist in multiple stress states and flow regimes in different domain regions. So the coarse graining is highly system-specific. And the knowledge, and in my humble opinion, that's even more complex than calibration. And the knowledge is simply not there. I mean, it's not, I would say it's rare amongst the software providers, so we can't really help our customers effectively because there's not too many experts with us. And then in the field, amongst the customers, there's also few. And so, more so than calibrating accurately, just the ability to simulate more particles would be the primary improvement in terms of accuracy in practice, in my view, and I would say in our view at Siemens. So that's why I have particles listed across accuracy, and both speed and accuracy, AI-assisted simulation can be used in some ways to accelerate to improve the computational efficiency. Right? And finally, there's ease of use. In terms of ease of use, our customers demand rapid setup in minutes, not hours, without reading documentation, and so on. So even a graphical user interface that is intuitive is not enough today. And that's because majority of our customers, DEM is just a tool in their tool belt. They're not DEM experts. They use DEM alongside many other methods. They can't devote a lot of time to DEM. And so they want it to be as easy as possible, as painless as possible, as black box as possible. And here we can help some with agentic AI, I was already mentioned. So again, I think the previous talks were excellent, by the way, in terms of detail. So we employ very similar methods, essentially, at Siemens. Okay, so simulation-assisted AI. Let's start here. And that's really about how to run fewer simulations using AI. So the idea of the reduced order model was already introduced. It was mentioned that measurement data is scarce, poorly formatted, could exist in an unstructured way in different parts of the organization. It's expensive to generate. It may have been generated. There's insufficient metadata. So even if you have measurements, it has not been documented under what conditions the measurements were performed, for example. So you don't know whether you can take measurements from different parts of the organization, put them together, and so many, many challenges. And the industry is not ready, I think, to solely rely on measurement data today across, at least in my experience. And so synthetic data has tremendous value. And we can derive that from DEM simulation or physics-based simulation method. And the advantage of having an AI-based reduced order model is this fast prediction of only what we care about. You know, some key performance indicator, maybe some warning, maybe some go, no-go condition, and so on. In our portfolio, we have a very large number of different methods. I'm not going to go into everything we have. We have multiple platforms, but I'll make a point that we can build our own from many different kinds of data, starting from static samples, you know, DOEs and the like. We can have 1D signals all the way to 3D signals and fields, and we have machine learning and AI methods that can model those different types of data and model it as a steady state ROM, so provide a static answer or a transient answer, so an evolution of some data. And as far as DEM is concerned, you know, mostly we use simple approaches. And Professor Windows, you already mentioned that you don't really need to use, I should say, actually, you can justify using a very complex method because with DEM, the data is quite scarce. I mean, if you have 9 static samples, really, you can justify using a neural network of any size. So you can use something simple, and I'll talk a little bit about that. But the one exception for us, actually there's two major exceptions, but one of those is if you have a time series data coming from EDEM, you know, you could have quite a few points in that signal. And then if you have multiple trials, then you actually accumulate quite a lot of data. And if you use all the data in that signal, then you can begin to see benefits from using neural networks rather than something simpler, you know, simpler meta model. And mostly we've been working with something called ROM AI, which, you know, the underlying idea is quite simple. We assume that the evolution of the signal obeys a very simple first-order ODE. And we further assume that the derivative, the first-order temporal derivative of that ODE is a function of a set of states, the derivatives of those states, and a set of input parameters. And then we use the neural network to simply predict the derivative in each time point of the signal. And we can construct the signal that way. So this is not a very complex idea, but actually in practice it works quite well. And this is really inspired by system control theory, and we have a bit of neural networks thrown in. I can give you more details on the algorithm, but I think you can probably figure out more or less how it functions. So this simple approach has been quite useful for us. I'll give you a simple example here with the beam blender. So, you know, we may have a full 3D model of the beam blender in DEM that could solve, let's say, in a day or so, because it's quite a long mixing time. And then we generate a relatively small number of data points, around 9 here, with different operational parameters. And then we can train our reduced order model with a graphical user interface, which is very simple to use. A non-expert can use it. You can make settings there if you know AI, but you don't have to necessarily. And then we can use that to very rapidly optimize the system. So you're seeing here real-time predictions of different operational parameters and the evolution of the segregation index. So we can explore many points in seconds. And what we find is that on average, with a surprisingly small amount of data, we can predict with sufficient accuracy for practical reasons, for practical purposes, the signals like that. So you can see here the segregation index evolution of an unfamiliar actually does the optimum that we've identified. And we can also extrapolate forward in time. So we didn't even show training data to a certain point, but the algorithm is able to also predict forward in time beyond the training time. And this helps do things faster. Now I should say that everything I showed you, and I'm not going to go into the workflow, but everything I showed you can be completely automated. And that's very important for our customers. And it can be completely automated in study engines. We have now, through the acquisition, 2 different study engines, HyperStudy and HEATS. But essentially, they do very similar things. So they can interface with the various tools. They can generate variants according to design of experiment configurations, or intelligently sample the parameter space according to some other algorithm. And we have a breadth of algorithms for that. Fit automatically reduced order models, including the large variety that we have in the portfolio. And then apply optimization algorithms of the kind that already were presented. The genetic algorithm actually, we find in practice has been most widely used and most effective because we can sweep the parameter space more thoroughly with the genetic algorithm than with something like a gradient descent-based algorithm. But you do have recourse to quite a lot, including you can write your own algorithms if you like and plug them in to that study engine. And then you can also perform some data analytics and so on. But essentially, we can wrap the whole process in a GUI and do things automatically. And we find that's key for the users always. How they use it. I mean, at this point, an obvious example would be calibration. So I won't go into that. It was already shown. So we can clearly calibrate using this method. But often they also perform geometry optimization, also similar to what was presented before. However, we can do morphing of the kind that was shown, but that's rare. First, the manufacturability argument was very good. We find our customers tend to try to stick to simple geometries and simple modifications. Also, you know, sometimes the outcome is counterintuitive, or you know, in any way they don't trust it, right? So they like simple changes, and I'll show you a simple example. But the important thing is that everything is automated and everything is, including the job management, right? And that should include cloud compute. So this is a very common, this is a toy example, but a very common case. So here we have a continuous mixer that we need to optimize. And we can produce a parameterized CAD geometry in one of our tools. And you can see that the changes are simple. Okay, it's just the size of pedals and their orientation. So again, we find morphing, free morphing to be rare. And then obviously you need to set up a base EDEM case. But after that, everything is automated. So the study engine takes over. It can produce the parameter, well, it can sample the parameter space, generate the cases. Crucially, it can send them to cloud, which is becoming extremely important today. We solve everything on GPU. I mean, 9% of our usage is GPU, and more on cloud. So the jobs need to be sent to cloud automatically. We don't want users to manually submit those, retrieve back, and then the meta model, the reduced order model, can be fitted iteratively, and we can apply the optimization on that reduced order model. And here, this is a result of a genetic algorithm, actually, where we explore thousands of evaluations very rapidly, but we really just train on 9 or 10 samples. And then we can arrive at some kind of optimal design. So in this case, the design is, the objective function is to improve the mixing efficiency. So very similar to what was shown, more automated, and the importance of high performance computing on GPU can't be overstated. Really, to achieve something in practice, you tend to need GPU for this kind of application. And here's a customer. So a real case. not exactly a continuous mixer. This is actually an aggregate dryer. One of our customers optimized this way with some help from us. And you can see that they were very pleased with the ability to perform virtual trials, help them optimize much faster and cheaper. And that's just one case that we can show. It's quite common to be able to do that. Now on the point about calibration, I mean, I already mentioned that really coarse graining might be an even greater challenge, but if you look at calibration, although we can automatically calibrate using the tools I just showed you, and it's not difficult to do, our customers are not satisfied with that. They really don't want to spend any time, any compute on calibration. And that's why we developed material model databases for them. And this is an example here. We have a built-in database in EDEM with thousands of material models for different responses. One is the FT4 rheometer basic flowability energy. Whether you like it as a calibration response, obviously it's system dependent. It's one of the popular tools out there. And by the way, on calibration, I should mention that the availability of the tests is crucial. So we may like to recommend quasi-static test and dynamic flow regime test together. We might like to recommend a wide range of stress, magnitudes. But really, the calibration is dictated by what's available, right? So even if you have guidance, and that's a great benefit to the community, by the way, I'm not saying it, but if you have guidance, that doesn't mean it will be followed, unfortunately, because not always do we have access to the measurements. But anyway, coming back to the databases, I mean, we just take it one step further where we pre-generate a very large number of results for them. So in this case, I train a ROM AI model to predict the temporal evolution of the cumulative flowability energy. And you can see that the accuracy is quite good, just on 100 training runs. This is the Edinburgh plastic model. So six parameters plus the interaction parameters plus the stiffness plus the density, so quite a few parameters, because the density also matters here. But with 100 runs, we can have this certainly good enough accuracy in practice. 3% error, maximum 9% error in certain cases. That's certainly compared to the magnitude of errors coming from elsewhere. That's excellent. And we can have thousands of data points generated, very rapidly once we have the ROM, and those get built into the product. So in our product, we have databases for different common calibration responses. We have flow energy, we have a direct shear test, just the steady state, so the pre-shear pointing and shear cell for now, static angle of ripples, and so on. The users can search according to their measurement, and we provide suggestions. And crucially, one is the mean particle diameter. Not everywhere, but our customers like to change size without thinking about coarse grain. And so it's very important that you can predict the response in terms of size, and that's actually the most challenging bit, to be honest. In fact, we have mixed success. So if somebody figures out how to predict better, that would be very useful, actually. Okay, so that's how we use simulation assisted AI. AI assisted simulation is more limited today. One idea which wasn't presented but we find extremely useful is to replace bits of simulation with AI. Again, ROM AI here. And if you look at this example and this is a very common example again, this is a coupled DEM multi-body dynamic simulation of a wheel load. And what we want to know is what was the sizing of the boom supporting the bucket, should be. And if you run the coupled job, it's very slow. However, you can run a few coupled jobs, and you can train a reduced order model to predict the forces on the bucket hinges as a function of the orientation, position, and velocity of the bucket. And then you can plug that into an MBD model only and remove the particles. So now you can run your design iterations. You can change the boom size, configuration, and so on very rapidly, because the MBD model runs 10 times to 100 times faster than the coupled job. And you can see that the prediction of the dynamic response is again good enough for practical purposes, especially we care about the peak, and you can see the peak is reasonably close prediction to ground truth. So this is a very common approach for us to speed up coupled simulations. And a real world example, excuse me, my clicker malfunctioning there. A real world example of that is this simulator for operator comfort at CNH. So this is a tractor that is towing a tillage tool. And originally, the motion of this, let me see if the videos will play actually, because I went backwards. So originally, the simulator was powered by a multi-body dynamic simulation underneath, which was fast enough to run real time. However, they wanted to improve the fidelity by adding in the tillage tool and the soil, because obviously that adds a lot of vibration. But the problem is now the simulation can't run real time. We can't be even close. And so we apply the same approach. We train a reduced order model, a ROM AI model, to predict the forces on the hinge of the tillage tool as a function of its configuration and also the saw properties. And we can plug it into the MBD model. So the MBD model now came back to running in seconds as before, and could again inform the operation of the simulator. And this prompted actually a multi-million-dollar investment by CNH in various tools because they found it extremely useful. And notice it's just 5 runs. So we only needed 5 runs to produce something that CNH found was good enough for them. And we had competition here, by the way, with different approaches, and this one turned out to be the most appropriate. So one other way that we're exploring now is to perform real-time extrapolation of the simulation and stop early. Similar idea, so we train on historic data, but we also train on the runtime data that gets exported during the solution. And so for this kind of approach, it's very important to have real-time export of data. But if you can do that, then you can dynamically train models and predict forecast, and stop early if you believe that you forecasted the steady state accurate. And therefore, you can save some simulation time. And if you have a DOE, initially you can't forecast at all because you just have the one run. But the more data points that accumulate in the DOE, the less time you need to actually simulate because you have more historic data for forecasting. And so we find that accelerates DOEs substantially if you have enough data points over time. So that's now, and in the future, we'd like to attempt real-time 3D extrapolation. Today we have geometric deep learning tools which are very good at predicting the temporal evolution of 3D field data. Here is an example of pressure distribution on a vehicle, for example, ground truth versus ground truth on the bottom versus the prediction. We have many examples like this. It's very popular now amongst our customers, but it obviously applies to continuum fields. So what we might attempt is to perform the continuum transformation in the usual way. Okay, compute the fields that we care about, what that we're permitted to compute first of all, obviously, but amongst those, the ones we care about. And then we can try to forecast the evolution of the continuum field, and then we might even try to rediscretize, and we might do that iteratively, for example. So that's an idea that we are going to start exploring. It's different to what Professor Schilder showed, but it's another idea of how we can have some AI-assisted solution, like accelerate the solver using AI. So we, in our case, we transform into a continuum first, and then back into a discrete, if possible. Of course, you have many challenges. So this is a Horizon 3 idea, I would say. Okay, finally, the last point is agentic AI. So how to set up simulations faster with AI. So, AI agents were introduced already, typically large language model based. You can have different levels of kind of fidelity of the AI agent or its capabilities. You can have a simple chatbot that just spews back knowledge. You can have a co-pilot that can set up things for you, and you can have an agent that is kind of semi-autonomous. And we're looking at a co-pilot at the moment. We don't believe that an AI, semi-autonomous AI agent is within reach, short term and even desirable, actually. But certainly a co-pilot is. And so similar to what was shown, we have a prototype of an AI agent for EDEM that actually should be a co-pilot for EDEM that can provide useful information and that can set up simulations. And you can see, actually, it's performing better than you anticipate. So if you look at a vague prompt, like make me an EDEM simulation of a 45-degree pyramidal hopper, and I don't have CAD geometry, make me CAD geometry, right? So you don't even give it the geometry of that. And by the way, it has never seen a pyramidal hopper, so never did we give it an example of that. With a few tricks, okay, to make it more robust, from that single prompt, it set up an entire EDEM simulation that runs, and it's very reasonable. It's close to what I would have set up as a first attempt. And it can perform. We're pleased. We're pleased with the performance. Pleasantly surprised. Possibly already useful enough to be released, amongst customers. So there's a lot of value, I think, in co-pilots. Now, the vision is to have automation across the entire digital thread, so-called, and that was mentioned also, by Professor Schilder, essentially. But it's a orchestrator agent, and then you have different specialist agents that work with the orchestrator agent to deliver something complex. We're working hard on that. In my view, that may be some way a way to be robust enough to be, applied, with customers broadly, so to be released in the wild. But we're working on that. That's the goal. Okay, now finish, because we're getting on time, with just our view on what is needed to position a DEM code well for AI. And there's input solver and output needs. So on the input side, we find a text-based input is essential. And it's very important that it's easy to parse and that there is a validation scheme. Okay, so ideally you would, and we find JSON to be excellent, actually ticks those boxes. But you need to be able to validate the input independently somehow, and it needs to be easy to parameterize. And then, crucially, you need to document it well for AI. And here we have a problem, because the paradigm is we're going to generate documentation with AI. But the problem is that the co-pilots then read the documentation to provide suggestions, provide advice. And so there's a really bad loop. Actually, you need people to write the documentation and to write it with AI in mind, because we find our documentation, for example, was very poor for AI. It needed to be written in a completely different format, specifically for the agent. So that's very important. Then on the solver, I already mentioned multi-GPU. We find multi-GPU is essential today. Okay, 90% of our customers use multi-GPU. It's 2 orders of magnitude faster on average. And you need to generate a lot of data, and so you need efficient solvers. What we find most useful in our solver, variable precision. That's been a game changer. So you don't have to have double precision everywhere. You should have hybrid precision, ideally. That is contact model dependent, so you need to analyze the contact models to find out which models and which parts of models can be single precision versus double, so that you don't lose fidelity. But that effort is worth it, because we see 30–40% speedups without almost any difference in results. Obviously, it needs to be memory efficient, it needs to be highly scaled. And then in terms of the output, a dense format helps. We need to generate a lot of data. It needs to be dense. Actually, storage is an issue for our customers. Variable write-out. We need great control over what is written out, not everything. Very granular control on what can be written out. Real-time export helps. And it should be fast to pass, obviously. Okay, so with this I conclude. I hope I told you something new. I follow excellent talks, so But thank you. Look forward to it.
Thanks very much, Stefan. Let's get about 10 minutes for questions.
So it's almost literally the last point you raised there around the dense output and needing lots of data. Going back to the point you mentioned earlier about doing the real-time predictions. How is the effect of, and I don't necessarily know what the real-time export means here, is that simply sampling every single calculation time set that you're using in your DEM and passing it to it, or doing a sub-selection of that, 1,000 hertz, 100 hertz, 10 hertz, whatever, as opposed to what your actual data set input, which might only be 1 hertz or something, and what's happening there, and how the noise that you might get if you take every single calculation point is being dealt with in the model.
That's an excellent question. So definitely you need control on the frequency of output. You don't want to output every time step. Rarely do you need. In EDEM we have frequency control. So the point is you can output in an easily parsable format, let's say CSV, just select results extremely rapidly, at very high frequency, without saving the rest of the simulation data. So you can't restart the simulation at that frequency, but that's not a problem most of the time.
But at what point do you at all start seeing that if your sampling frequency is too high that you're just introducing noise into the...
Yeah. You do that, and the way we deal with noise, I didn't touch upon it. Obviously, preparing the data for any sort of model fitting is crucial. So we have filters, and then we filter it after. And definitely you should filter it. I mean, if you have a lot, so any AI struggles with, if your signal has massive number of inflection points, that approach that I showed struggles a lot. Right? There's a different approach that you can take, neural ODEs and so on, but with that you still need a lot of data. So you definitely need to smooth it, no question.
You have shown these huge number of simulations where you build up your reduced order numbers for calibration prediction. That was quite interesting. Do you also, these reduced order methods, are they all of the same structure? And do you think about maybe also combining them in the field of, for example, ensemble learning or a prediction of new reduced order models without doing the simulation? If you already have a huge database, maybe you can have the first shot.
Yeah, that's a great point. That's exactly what I did initially, so around 5 years ago. So here we just have 100 runs and we make a large number, and that's enough. But for the annual repos, which was the original calibration test, in industry, that's 90% calibration for good or for bad. We had about 14,000 data points. And the challenge there was the size. I mentioned size. So we have 14,000 data points at 4 different sizes. What if you have a size in between? So we try to use all the data, but interpolate between sizes. And even with 14,000 data points, and this was JKR, so a relatively simple adhesion. Most of history depends on how it's important. Same shape and everything, it still struggled to predict across sizes. So the greatest challenge we find actually is size. So if you have ideas, I'll be happy to hear them. Professor Gouverneur also has some papers on that, but he also struggled a bit to span the size. So the size question is the primary challenge for us. We want to be able to give them the parameters for any size. Granted that obviously the coarse grain system dependent, but at least for the response, forget whether it's applicable when you move to a flow regime or whatever. If we can give a prediction for a different size and cycle, that will be great. We have mixed success. It's very, very pretty. And there maybe we can explore some of those methods. So I will reach out. Great point.
I was going to ask one. So historically, and I'm going back a bit here, it could be quite difficult to get industry to buy in, let's say, to DEM, right? Because it was using spheres, and they're not capturing shape and so on. It's idealized in some way. But over time, gradually, they come to accept, of course, through software like EDEM especially, that it has value and is useful. I'm kind of curious about how industry have bought in to DEM plus AI, because also out there's a lot of skepticism about AI, I guess, in some sense.
Yeah, no, it's so excellent point. You know, people don't trust simulation necessarily a lot. Depends on the sector, but there is in certain sectors great degree of conservatism. So even simulation in general, difficult to sell. Then DEM, you know, the challenge of particle size, the fact that it doesn't look like the real material is a challenge for a long time. How do we go about it? I mean, my experience is I typically perform a proof of concept, right? So I work with a customer and we solve a problem. And then they show to management the problem is solved. And that's been really the only way that I've been successful. I have had a few successes over the years, but it's always been the same approach. So we do a small project, we calibrate, validate, solve a problem, and then they show it to management. That helps them buy. So that's how we go about it. And then the shape, I mean, the shape is being a massive headache for us because you have so many sources of error in DEM that you know, accurately approximating the morphology, you know, in academic context is extremely important, but in practice, you know, considering all the other errors that are inherent in, you know, it's a minor consideration. But the competition was very vocal about using particle, you know, exact particle shapes and so on, although they're very slow. Yeah, we struggle. I mean, again, a major blocker for us is the small amount of knowledge out there about DEM and grinder mechanics that is, you know, digested for that audience. Right, so I don't have to send papers, which don't get read, but I can send a 200-page book, which is simple to understand. It says, look, you know, most of the time multi-sphere is okay for practical purposes. So, you know, you go to the exact morphology only if you care about, let's say, microstructure or, you know, hyper. I mean, there's many times that you need to care about it, but not always. So something simple that we can refer to would be excellent, because now we send papers and not always do they get read.
So, for example, in one of the cases I think you showed was the bucket one, and you've just done, I think, probably, incorrect me if I'm wrong here, but you may have done multiple parameters on the bucket to get to that different friction parameters or something, and then found a decent set of parameters and train the model. Is that correct? And then just use the reduced order model of it. But in that particular example, the point I'm getting to is that you can use the AI to do a parameter sweep, and you get a set of parameters. So it comes out, it's like static friction 0.5, rolling friction 0.5, restitution 0.5. Perfect. That's my material. Do you then just take one run on that, or would you take multiple replicates at the same one? Because when you change the filling, the static generation, whatever, with the same parameters, you'll get different response, and you get the natural variation noise, and that you introduce multiple runs at the same parameter set to capture that variability, or is it always just one run, one set of parameters?
No, it's a great point. I mean, in this case, you didn't have that much variability, but if you do, then you need some kind of average, no question. So you need to, yeah, and you need to smooth that.
And say HyperStudy will handle that for you. Allow you to set
you can automate it in HyperStudy. You can automate it in HyperStudy. So it's very flexible. In Heats is the same. You can do almost anything that you like, really. You can trigger whatever executables. You can perform whatever manipulations on your data and so on, including third-party tools. So you can automate that. That'll be trivial to do, but it's important, as you say. I mean, stochastic effects. You can analyze stochastic effects, and it can make decisions. So if it, for example, you can tell it, listen, estimate the stochastic effects. And if they're above a certain threshold, perform additional runs, take means, and do that until you're happy that the variance is within some acceptable, coefficient variance is acceptable. You can tell it that. Yeah.
Any other questions for Stefan?
Early on, when you discussed the needs of industry and the gaps and so on. You mentioned of the need for accuracy, and you said that the gap is between currently millions and the need for trillions of particles. But besides the practical aspects, would trillions of particles give accuracy? And you know, within the context of AI, I would expect that actually you would use the AI to reduce the number of particles you need rather than increase them. So not to reduce all the modeling to the level of a simple function, but you know, use some AI tricks, some AI kind of automated processing to tell me what is the least number of particles I need, rather than kind of saying that, oh, let's run with trillions and hope for accuracy.
I mean, that's a great point. So if we can tell them what size to use safely, then you're right. And if you have an AI that can handle that, although I think, again, it's very system dependent and extremely complex, so I'm not sure how simple it will be to recommend the size. You know, you have bottlenecks in the geometry, you have to consider the inertial effects, you have to consider, you know, maintaining the stress state, you know, the kinetic pressure especially and stuff, you know, the higher sizes. I don't, if it certainly worth, so if you tell me that you can do that, then we'll be very happy, and that comment will change. But in the meantime, in the absence of something like that, the ability to just, for them to just blindly go as close as possible to the size is the safest approach, you know.
It would make them feel safer, but is it safer? Is it actually going, you know, is there any indication that just size is enough to get accurate?
No, of course not. No, that's not the point I made. I just made the point, and you know, the comments about calibration are extremely valid, and you know, I completely agree with the assessment, you know. But I'm just saying that size is, you know, the effects of size and blindly increasing size are even worse. So, you know, we need a way to you know, reduce that problem. Of course, then you also want to calibrate well and so on. So none of the other sources of error is significant. It's just, in my view, this is a very significant one.
Perfect. Thank you, Stefan.